Let's start with a simple idea. In science, knowing something is often not enough. We need to know it precisely. That's where High Resolution Mass Spectrometry, or HRMS, truly matters. HRMS acts like a powerful detective tool, helping scientists uncover the true identity of chemical compounds, even in extremely complex samples. Whether it's drug discovery, environmental analysis, or forensic science, HRMS provides the confidence needed to say, this is exactly what we're looking at. This is why HRMS sits at the intersection of precision and discovery, where accurate measurements lead to meaningful scientific breakthroughs. To understand why HRMS was such a breakthrough, we need to look at the limitations of low-resolution mass spectrometry. Low-resolution instruments can tell us the nominal mass of a molecule, but here's the problem. A mass of 300 doesn't point to one compound. It could represent many different chemical formulas. This is like trying to read a book with blurry text. You can see the outline, but the meaning is lost. HRMS solved this problem by distinguishing masses that differ by only a few millionths of an atomic mass unit. That single improvement transformed mass spectrometry, from a rough screening tool into a definitive identification technique. So what do we actually mean by high resolution? In HRMS, resolution refers to the ability to separate ions that have nearly identical mass-to-charge ratios. For example, compounds like C2H4O and CH8N both have a nominal mass of 44, but chemically they are completely different. Now add mass accuracy to the picture. Modern HRMS instruments achieve accuracy within 1 to 5 parts per million. That means when the instrument reports a mass like 300.1234, you can trust it. This level of precision allows scientists to determine exact molecular formulas, which is the foundation of confident chemical identification. Every HRMS system works like a well-coordinated team. Each component plays a critical role. It starts with ionization, where molecules are converted into ions, often using soft techniques like electrospray ionization or MALDI, so the molecules remain intact. Next comes the mass analyzer, the heart of the system, where ions are separated with extreme precision using technologies like TOF or Orbitrap. Finally, the detector and software record the signal and convert it into usable spectra. Understanding this workflow isn't just theoretical. It helps analysts troubleshoot problems and optimize performance in real laboratory settings. Not all HRMS instruments are the same, and choosing the right analyzer is crucial. Time of flight, or TOF analyzers, are fast, robust, and ideal for broad screening applications. They're excellent when speed matters. Orbitrap analyzers offer exceptional resolution and mass accuracy, and are widely used in proteomics and metabolomics, where complex biological samples demand high confidence. At the top end is FTICR, the gold standard for resolution. It delivers unmatched performance, but comes with higher cost and complexity. The key takeaway is simple. Choosing the right analyzer isn't about prestige, it's about matching the tool to the analytical question. HRMS truly shines when applied to real-world problems, especially when answers are not obvious. In pharmaceutical research, HRMS identifies drug metabolites at trace levels and characterizes impurities that could impact safety. In environmental science, it detects unknown pollutants in water and identifies contaminants in soil, even when standards don't exist. In forensic analysis, HRMS helps identify new psychoactive substances, often before reference libraries are available. This is why HRMS excels when the question is complex and the answer isn't obvious. One of HRMS's greatest strengths is unknown identification. By combining exact mass measurement, isotopic pattern analysis, and fragmentation data, HRMS allows scientists to reason their way from a signal to a molecular formula, and often to structural features. This is especially powerful in non-targeted analysis, where you don't know what you're looking for in advance. In this way, HRMS becomes more than an instrument. It becomes a scientific reasoning engine, guiding analysts toward the truth hidden in complex samples. Although HRMS is best known for qualitative analysis, it's increasingly used for quantification as well. Accurate mass measurements and isotopic pattern analysis support reliable quantitative results. However, success depends on practical factors. Matrix effects can influence ionization efficiency. Instrument stability is critical for long-term studies, and advanced data processing is required for accurate peak integration. In practice, strong experimental design and thoughtful data analysis are just as important as instrument performance. Despite its power, HRMS is not without challenges. The high cost of instruments, complex maintenance requirements, and massive data files can limit accessibility. Data interpretation also requires highly skilled analysts, and regulatory validation may demand extensive effort. These factors impact implementation and require strategic investment planning. Understanding these limitations helps ensure HRMS is used where it delivers the most value. Looking ahead, HRMS is becoming faster, smarter, and more accessible. Advances in automation, software, and artificial intelligence are transforming raw spectral data into actionable insights. High Resolution Mass Spectrometry provides the confidence scientists need, where precision meets discovery. Thank you for your attention.